Besides having the value of the option, it's also important to have how sensitive is this value of the option as a function of the different variables we have in the problem, which is time, asset, price, and also some parameters we have appear in the Black-Scholes equation. And we'll use that Greek letters for that. That's what we'll call that the analysis of the Greeks. So the first one is the partial derivative of V, the option, with respect to the asset, which shows how sensitive is the option with respect to asset. And this one is called delta. And remember that this is the one that appears in the delta hedging, which basically means that holding one long position of the option and one short of a quantity delta of the underlying. Of course, as time goes by, the S value varies, then the delta you have to consider will vary as well. That's what's called the dynamic hedging. So you have to change delta as S changes as well. And if delta is very big, then it means that probably the delta hedging will collapse, because we probably need to consider other contributions to the variation of V with respect to S, which goes into higher order in S. And that's where the gamma, which is the second order derivative of V with respect to S, enters. So gamma is showing the sensitivity of the delta here with respect to the underlying, because this is the partial derivative of delta with respect to S is equal to the second order derivative of V with respect to S. So basically means it's indicating how often a position must be rehedged in order to maintain a delta neutral position. And the hedging requirement is decreased usually by a gamma neutral strategy. So these are two of the Greeks, probably the most well-known Greeks we have associated with the value of the option. But there are other ones. For example, here we have theta, which is the partial derivative of V with respect to the time. And this is a term arises in the Black-Scholes equation, for example, and this contributes to ensure that the delta edge position earns the risk-free rate, because this term appears in the Black-Scholes equation and multiplying times with an R, which is the risk-free rate. Then another one is called the vega, which is the partial derivative of V with respect to the volatility. Here is not a variable, it's just a parameter. And this showing the sensitivity of the value of the option with respect to the volatility. So here we have a derivative with respect to a parameter, and the value of the parameter, of course, is not completely known. And here we don't have the partial derivative of V with respect to the variable. So sometimes we can also vega H in order to reduce the sensitivity to the volatility, which might be the major step to reduce the model risk, because the volatility is the same parameter that arises in the model, in the log normal hypothesis you're considering in order to describe the stochasticity associated to the asset. So if you want to reduce the implications of the model or the risk associated to the model, you can also vega H. Or another one here, we have the partial derivative of V with respect to the interest rate with respect to R, and this is called rho. And this shows again the sensitivity to the interest rate, and sometimes also in order to evaluate in these Black-Scholes equations, sometimes can be the whole term structure of the interest rates is also used in order to describe in order to price the option. So here we have presented some of the Greeks that are used in order to analyze the sensitivity of the option that we have evaluated through this Black-Scholes equation. The sensitivity of the option value with respect to the time, with respect to S, which are the variables we do have in the problem, and also with respect to the main parameters we do have in the model, which are the volatility and the interest rate.